Hello students. Hi, welcome back to Vedantu NEET English. Welcome back to your chemistry class. Welcome back to your inorganic chemistry class specifically. My name is Nandini ma'am and today we are going to learn about P block. We are starting P block for your NEET 2024 exam. But before that, let me know if you can see me and hear me clearly. Hi, good afternoon, Vardhan. Good afternoon, Pradeepa. Hi, good afternoon. Please let me know. Yes, bacha, this is Super 6 sessions where we're going to discuss 10 years of PYQs. Actually, I've included even more, 15 years of PYQs I've included in this session. We are going to do line by NCERT. Also, whatever are the possibilities of any questions that can be asked in your NEET exam, we're going to cover each and everything. After this exam, after this session, you can be very certain about solving each kind of PYQs that can be asked in your NEET exam. All clear, Vardhan? Chalo, let us begin. Yes, all perfect. So I'm getting perfect responses. So today in this session, I already told you P block, we're going to start with 13th and 14th group. Okay, before we do that, let us look at the syllabus because now you have reduced syllabus. So we are going to study according to that syllabus. So let us look at that. Okay, everybody can see my screen. So in your P block, what is there? From group 13 to group 18 elements are there. And what are the things that will be asked in your exam? The entire P block chapter will not be asked. Only these topics which are mentioned in your new reduced syllabus according to NEET will be asked. What are those? Those are electronic configuration will be asked of each block. Their general trends, what are they? Their atomic radii, density, melting point, boiling point, ionization radii, ionization energy, and what all? Okay? And their chemical properties of elements across the period and down the groups. What are the chemical properties? In every group, we are going to study 3 types of chemical properties, 3 types of chemical reactions. With every element, we are going to study their chemical reactions with number 1, hydrogen, number 2, oxygen, and number 3, halogens. So all these 3 chemical reactions are there in your course. And the next is unique behavior of the first element in each group. So whatever in the P block elements, the first row is what? The first row is the second period. So every element of the P block in the second period has some anomalous properties. What are the reasons for that? What are their properties? All this is in your course. Okay? It is very much reduced. Last time what happened, even compounds of all these, like compounds of 13th group, compounds of 14th group were in your course. Okay? So accordingly, we are going to study according to the reduced syllabus. We're not going to study those compounds, but I'm going to teach you specific important structures which are there in your compounds, but we're going to study only the structures because there is still a possibility that those structures can be asked looking at the trend how the JEE 2024 was made, because JEE 2024 again was made according to the reduced syllabus. So we are following even that, okay? Because NEET follows the JEE pattern always. Remember that. We are going to continue. Beta, we have done coordination compounds. Somebody is asking, ma'am, when coordination compounds? It is already done. You can check on this channel. I've completed everything about the coordination compound. It's a perfect chapter to look at. Okay. You can watch. And now let us begin. Before I start, I again want to clarify about some resources because I know students on this channel are very NEET oriented. So if you are looking for resources, then you can check out those links. You can check out the Telegram section that is in the description box below. You can check on that. You'll get all the PDFs, notes, important announcements. Everything will be there. The other things, all the PYQ tests, PYQ PDF, CBSE, all these links are attached below. You can check them out. The next thing is, okay, and if you want the most difficult question on any topic, then also it is linked in the description box below. one most difficult question each day. You can check that out again from the description box below. The next thing, that if you are someone who cannot concentrate online, if you're studying online, then there is no schedule of yours, right? You are not embedded in any schedule, and hence your studies are impacted. Because if you are someone who needs to be disciplined and needs some offline help, then again Vedantu brings to you. Sorry about the noise. Let me, let me mute that. Hanji. So you can check the IVSAT scholarship exam. You can take this, and if you belong to any of these cities, right? If you are near these cities or belong to any of these cities, then you can join the Vedantu offline center for your NEET 2024 preparation. Again, all the links are in the description box below. All these are for your resources. Now let us begin the chapter. Let us begin the chapter. Beta, right now we're going to cover the 11th class P block chapter. Okay? 11th class P block, 13th and 14th group. So first of all, whenever I begin with the P block, I always tell students to have this periodic table embedded in your head. It is very, very crucial. You should know that this one is the S block elements, right? These one are your transition elements or your D block elements, right? This one are your inner transition elements or your F block elements, okay? And all these are your P block elements. So this periodic table should be embedded in your head. We start with the S block, then we go till the P block, correct? Now I have one question for you guys. The question is the element here, that is helium. What is the electronic configuration of helium? The electronic configuration is 1s2, right? So if helium a P block element, let me know in the comment section below. What do you think? What is the status of helium? Is helium P block element? Okay? That is your question of the day. You can just answer me in the comment section below or in the chat box, whatever you feel like. And why do we call these P block elements? What is the reason behind it? We are going to study now. Okay? Before getting introduced, what are P block elements? Why are they called P block elements? Why are we studying P block elements? You have to know that P block elements are so useful. For example, can you see a pencil here? The pencil with which you've been writing since your day one of school. The pencil has graphite in it, right? And graphite is nothing but an allotrope of carbon. Carbon is a P block element. Next, can you see the aluminum foil here, which your mummy wraps food inside whenever you go to school. So aluminium is again a P block element, right? Now, can you see what kind of jacket this is? This is a bulletproof vest. Bulletproof vest, bacha, is made up of boron and nitrogen, which is called boron nitride. Both of them, boron and nitrogen, are all your P block elements, right? And can you see this mirror? This mirror. So mirror, now what is mirror made up of? Mirror is made up of actually silver. You'll say, ma'am, mirror is made of silver, and silver is a D block element. But silver, what happens to silver? For example, if you wear silver in your leg, especially in the form of pile, people wear that, right? As a form of anklet, you wear silver in your feet. What happens to that silver? It actually gets black with time, right? It tarnishes in air. But does that happen to your mirror? Does your mirror tarnish? No. Why? Because the mirror that is used in your homes is actually fused with aluminium vapors. Remember this, aluminium vapors, and that's what makes your mirror appear flawless till the end of the time, right? For years and years, it never gets tarnished due to aluminium vapors in it. So what are these? These are the uses of the P block elements. You must know in your everyday things, you see P block in your pencil, in the aluminium foil, in the bulletproof vest, and even in your mirror. Everything is made up of P block elements. Okay? Let us begin the next thing. Yes, now why do we call them P block elements? We call them P block elements because of their number first electronic configuration. What are the electronic configuration of P block elements? First of all, know that they begin from group number 13 to group number 18. Remember this. What group do they belong to? Group 13 to group 18. Correct? And what period do they belong to? From period number 2, 3, 4, 5, 6 and 7. So they belong to the period. Which periods do they belong to? They belong to period number 2 to period number 7. Understood this thing? Okay? And they are called p block elements because of their electronic configuration. What is the electronic configuration? Electronic configuration is NS2 NP126. Remember this. Okay? This is their outermost electronic configuration because the outermost electron enters the p subshell. Okay? P subshell has how many orbitals? This is your p subshell, right? This is your p subshell. It has 3 orbitals. Can you see? 1, 2, 3. P subshell has 3 orbitals and each orbital can contain a maximum of 2 electrons, right? 1, 2, 3, 4, 5, 6, right? So the maximum number of electrons that the p subshell can have is 6. Hence, there are 6 groups of p block elements. This is why we have 6 groups of p block elements due to their electronic configuration, due to their outermost electronic configuration. This thing you must all keep it in your mind. Okay? The next thing that you should know is their oxidation state. What is the oxidation state? Bacha, oxidation state is the sum of s plus p orbital. This is the maximum oxidation state. What is the maximum oxidation state? For example, we're talking about, let us go back to the 13th group. So 13th group has in p orbital only 1 electron, right? 14th has in p orbital 2 electrons, 15 in p orbital 3 electrons, here it has 4, here it has 5 and here it has 6. Okay? So these are the electron configuration of p orbital. That is it. Only p orbitals are mentioned over here. Okay? Now what will happen? Let us go back to the next slide. In the 13th group, I told you that there can be how many electrons? NS2, NP1. Correct? So the total number of S and P electrons, how many are there? There are 3 total number of electrons. Hence, the maximum oxidation state that group 13 can show is actually 3. So, can you see group oxidation state? So, the group oxidation state of group 13 is plus 3. Similarly, for group 14 is plus 4. Similarly, for 15 is plus 5, plus 6, plus 7 and plus 8. So, what is that? It is nothing but the addition of the total number of electrons in the s and the p orbital, and that is your group oxidation number. So the group oxidation number actually is true for which elements? For which elements? For your second period elements. For example, what is the second period? For example, the first member of the p block. This is true for boron, for carbon, for nitrogen, for oxygen, for fluorine and for helium. For helium it is not. Let's start with neon. Okay. For these elements, these oxidation states are true. But what happens when you go down the periodic table? Then actually their oxidation states keeps on reducing. How much can they reduce? They reduce by a factor of 2. Remember this. What is the difference between the oxidation state? For example, a group 13 can show 2 oxidation state, which is plus 3 and plus 1. So there's a difference of 2 oxidation states always. Similarly, group 14 can show plus 4 as well as plus 2, and minus 4 is shown by just carbon. Remember this. Similarly, group 15 can show plus 3 and minus 3 oxidation states. So difference is again of plus 2 oxidation state. Remember this. Okay? So a difference in oxidation state when we go down the group is of 2 units. Okay? This is what you get out of this graph. And as you go down the group, what happens? The smaller oxidation state becomes more stable. Let us look here again. So when I go down the group, the smaller oxidation state, for example, plus 1 for group 13. For group 14 will be plus 2, will be more stable. As you go down the group, the smaller oxidation states become more stable. What is the reason behind it? I will let you know as we proceed further. But right now, know these specific things. Okay? What is the next thing? The next thing that you should know is the metallic character of all the p block elements. So in general, the general trend, if somebody asks you a general trend of p block, I'm not talking about any specific group. I'm not talking about group 13, 14, 15, whatever. I'm talking about general for the entire p block. What happens? What happens when you move along a period? What happens to the metallic character? What happens to the metallic character? Metallic character actually decreases. Okay? But when you go down the group, the metallic character actually increases, which means what? The elements which are present ekdam at the end of the periodic table, at the down, are the most metallic elements. Remember this thing. The elements that are present at the below of the periodic table in p block are the most metallic, and we know as we go down the group, heavier elements increases, right? These are what? These are heavier elements. Hence, heavier elements are more metallic in nature. Remember these things. These are some facts. Sorry, yes. So these are some facts that you should know, because inorganic chemistry is filled with facts. But I'm going to teach you the reasoning behind each and everything. Now again, a very interesting fact is P block is the only block, because we have talked about this. F block, D block, F block. So I'm going to tell you another very interesting fact. All the other blocks, whether it is S, D or F, all of these are made up of just metals. Just metals. S block, D block and F block. Only in P block you will find metalloids as well as non-metals. Okay? Only in P block there is a combination of metals, non-metals and metalloids. And what are the metals? What are the non-metals? What are the metalloids are written over here. Okay? Group wise, when we are going to study, I'm going to tell you which one are the metals, which one are the metalloids and which one are the non-metals. Okay? Right now, for your convenience, it is written over here. Everybody, hi, hello. Okay? Everybody understood this point? Now the next thing that you should know while looking at the periodic table is, bacha, this is your first series, right? This is the first period. In first period, every element just have two orbitals, which is s orbital as well as your p orbital. Okay? Only two orbitals are present. But as you go down the group, as you go, for example, in aluminium, what happens? From aluminium, there are three orbitals present, S, P and D. Remember this. So what I'm saying, from the third period, what happens? Another block enters, which is your D orbital. And due to that, the properties start to change. This is what makes the first element of any P block a anomaly. Anomaly means what? It is different than the rest of the elements, right? Why? Because the first element of each P block contains only and only S and P orbital, but from below that there is another orbital D block enters inside it, and hence its properties entirely changes. Therefore, the first period elements, the first elements of each block of each group shows the anomalous properties. Everybody understood this? Everybody understood this? Okay? And the next thing that you should know is, because the D block enters over here, what happens? What happens? So this only forms, the S and P orbitals are only there. So this only is capable to form p-pi bonds. What are p-pi bonds? For example, the bonds that you find in C double bond C, your C triple bond N, your C double bond O, right? So whenever these elements react with themselves or with the other first elements of the same block, they form p-pi bonding, right? But below the group, they can form d-pi bonding. D-pi means what? That it can form d-pi or d-pi bonding. So all these bondings are present below the group. Everybody is understanding this point? If you have any confusion, then let me know. So what happens? The maximum covalencies also changes. We're going to talk about it in the next thing that we're going to study. The other thing that I want to tell you when I was talking about the non-metals and the metals, one thing I forgot to mention is how will you know which is the most metallic and which is the most non-metallic thing? How will you know that, bacha? ठीक है, the metallic oxides, remember this, the metallic oxides are always basic oxides, right? And the non-metallic oxides are acidic oxides. ठीक है, always remember this basic point. Whatever metals will be there, their oxides will be basic in nature. Non-metals oxide will be not basic in nature. ठीक है, the other thing that you should know is that the non-metals actually are famous for what? They have high ionization energy as well as high electronegativity. Remember this thing. All the non-metals have high ionization energy and high electronegativity, while it is not true for the metals, right? That's why non-metals always form anions, right? While the metals form actually cations. So all these are basic things that you should know. Basic fundamental things that you should know, which you've been studying since your 9th, 10th class, right? All the metal oxides are basic, non-metal oxides are acidic, right? And the non-metals actually have higher ionization energy, higher electronegativity, and hence they form anions, while the metals actually form cations, right? You can actually see how metals form anions. What metal do you know? I know aluminium +3. Aluminium is a metal. It is forming a +3. That is a cation. Similarly, sodium, which is a metal, forms Na+ cation. Similarly, magnesium, which is a metal, forms Mg+2 cation, right? And what are the non-metals? Non-metals are, for example, your fluorine is a non-metal. It forms an anion. Your chlorine, which is a non-metal, forms an anion. So you can remember these things by remembering these kind of examples, right? Similarly, your oxygen is a non-metal. So non-metals form anions while your metals form cations. You can understand them by these examples. Correct? ठीक है? Ma'am, is prep and prop not there? What is that, bacha? I didn't get you end game. What are you trying to say? What is prep and prop? Preparation and properties, are you saying that? Achha, properties are going to be there, but preparation is not there in your exam anymore. I just discussed the syllabus. We're going to go with the new syllabus, not the old syllabus. Correct? Now, introduction to group 13. We have discussed everything that is there to discuss about P block in general. So what did I discuss about P block? That the metallic character actually decreases along a period but increases along a group, right? As we go down, metallic character increases. As we go down, heavier elements increases, right? And the first elements of each group actually has only p orbitals. Hence, they can form only p-pi bonding. But from below that, we have the d orbitals there in their electronic configuration. So they can form d-pi, p-pi and p-pi, d-pi bonding. So these are the basic things that you should know about p block elements. And what is the other thing? That the p block elements are the only group. P block is the only block which contains all three kinds of things, which is metals, non-metals and metalloids. These are the important things. Now let's come back to group 13, right? Group 13 has what elements? It has boron, aluminium, gallium, indium and thallium. In your NCERT, there is abundances given for boron and aluminium. Very important because it is asked every time in exams. I will show you an example with the PYQ. We're going to solve the PYQ and I will show you that every of these abundances are so important. Okay? Boron actually exists in two kinds of isotope, which is boron 10 and boron 11, right? And boron 11 is actually 81% present and boron 10 is only 19%. Next thing that you should know is it is a very rare element. Boron is very rare in Earth's crust. Only 0.001% by mass it is present. Next is minerals. What minerals is boron found from? It is found from the orthoboric acid. The formula is H3BO3, very important, orthoboric acid. It is a kind of acid, correct? Orthoboric acid in your exam, to confuse you, can also be written in this form, BOH3. And what you will do, they will ask you, ki bachcha, this is the formula. Now tell me, is this a acid or is a base? So what you will do, you will see the OH here and you will say, oh, OH is there. Hence it will give OH minus sign. Hence it is a base. Wrong. This is actually a acid, right? Why is it an acid? We're going to discuss right in this session. But abhi ke liye, know this, that this formula can be written like this also in your exam, just to confuse you, right? The next is borax. What is the formula for borax? You should know it is Na2B4O7 dot 10H2O. The kernite is another. If it's mineral, its formula is same, Na2B4O7, only the water molecule is different. Here only 4H2O is present, right? And where it is found in India, borax occurs in Puga Valley, which is in Ladakh, and Sambar Lake, which is in Rajasthan. So what is the best way to remember? Ladakh is a cold desert and Rajasthan is a hot desert. So boron is actually found in both type of deserts, in the cold and the hot. So cold is Ladakh and Rajasthan mein Sambar Lake. Okay? So in this way you can remember this thing. Now next is aluminium. Very important. It is the most abundant metal. Remember this. Most abundant metal. Okay? And the third most abundant element after oxygen and silicon. Right? Oxygen and silicon, it is 8.3% by mass after oxygen and silicon. Very important. Next is, what are its minerals? Bauxite, which you've been studying since your 9th class, 10th class, 8th class even, right? What is the formula for bauxite? Al2O3.2H2O, and cryolite, the formula is Na3LF6. How is it found? It is found as mica in Madhya Pradesh, Karnataka, Orissa and Jammu. Very important slide. I'm going to show you the importance of what we just said. NEET 2022, just a year back, this question was asked. Match list 1, match list 2. If you knew all the minerals, you would get a +4 marks. Remember, all of these things which I'm teaching you, very important. After this session, you do not need to look at your NCERT again, because everything I've included over here. Just take these notes because these will be crisp and clear. You don't have to read to the theory of NCERT. Just go through these notes, because even 15 years of PYQs are mentioned over here. Now, what is borax? Now you have to match these columns. Okay? Another important question which you can match. We just read what was kernite. Kernite was Na2B4O7 or 10H2O. Orthoboric acid is H3BO3, right? What is borax B? What is kernite and what is borax? All of these things you should know. Okay? Can you match this thing? Can anybody match this thing? Okay. It is a tribasic acid, Pavish is saying. Very good. So you can do this as a homework. Hai na? Again a PYQ. Next, let's move forward for the electronic configuration. Very important. Whenever we are going to read about P block, we are going to look at all the elements electronic configuration. It is extremely important. As I said, boron, the first element, will be the anomaly. It only has 2 orbitals, 2s and 2p, right? And your d orbitals actually, and aluminium actually has vacant d orbital. Remember this thing, okay? It has vacant empty d orbital, which means what? That it can form more bonds among itself. But your boron has no d orbital. So this is the difference between these two things. From gallium, your filled d orbitals begin. Can you see? From gallium, d orbitals are there, and in thallium, your f orbitals are introduced, right? So its inner configuration is actually changing. Can everybody see? The outermost electronic configuration is Ns2Np1, right? Ns2Np1 is the outermost electronic configuration. This is the s orbital, 2 electrons here, and in p, just 1 electron is there. This is their electronic configuration, right? And nahionium, bacha, here is a radioactive element, and its half-life is just 10 seconds. Remember this, is just 10 seconds. Okay? And then let's move forward. Now, before we look at all the properties, we have looked at the electronic configuration. What did I tell you? I told you that here in gallium, d orbitals are introduced. Here in thallium, f orbitals are introduced, right? The ns2np1 configuration is called the outer electronic configuration, which will participate in bonding. These s and p orbitals will participate in bonding. These are called outer electronic configuration. But this introduction of D and F is called the inner electronic configuration. And due to the introduction of these two orbitals, which are very, very poor shielders, so many of the properties you will see changing for gallium and thallium due to the introduction of the D and the F orbitals. I'm again and again mentioning, please keep them in mind. Okay? Now we're going to talk about properties. Before that, understand how properties generally vary in a periodic table. What happens when you go from S block to P block? The size actually decreases. There is a decrease in size. If the size is decreasing, the ionization energy. What is the ionization energy? This is your nucleus and this is the electron. This is the shell outside the nucleus. So the energy required to take out the electron from the outermost shell is called the ionization energy, right? The energy required to take out the electron from the outermost shell is called the ionization energy, and along a period, this energy actually increases because the size is decreasing. If the size is decreasing along a period, what is happening? The electron is coming closer to the nucleus. Hence, it is very, very difficult to take out that nucleus, right? To take out that electron away from the nucleus. Hence, the ionization energy increases till the P block. Electronegativity also increases from S block to P block. Similarly, down the group, let's talk about. As I'm moving down the group, what will happen to the size? The size will actually, what will happen? It will increase down the group because one shell keeps on adding. What happens? Here there is only one shell. Here there are two shells, then three shells, then four shells, right? So what is happening as I'm moving down? The number of shells are increasing, hence the size is increasing down the group. If the size is increasing, what will happen to the ionization energy? The ionization energy will decrease because now the outermost electron is so far away from the nucleus, hence it is easier to take it out. So the ionization energy decreases as we go down the group. It is a very, very important slide that you should consider. Electron affinity, electron negativity, everything is mentioned. Okay? Electronegativity increases along a period but decreases down the group, which means what? The elements present below the group are actually metallic in character, and the metallic character increases and decreases diagonally. Look at this slide. We are going to move forward. Next trend. Number first trend of your group 13 elements is your atomic radii. Very, very important. Thank you, Sarat. Thank you, Sarat. So what is atomic radii? So what happens? We are going to study each group wise, right? So boron has only two shells, right? Aluminium actually has three shells. But do you remember what happens? In gallium, there is an introduction of d orbital. So what happens with d orbital? As soon as the d orbital is introduced, the size actually shrinks. The size becomes small because d orbitals are poor shielders. So what is the order of atomic radii? I'm going to write it over here. It is not given directly in your NCERT. It is given in form of values, but we are going to form a trend. Because in your paper, what happens? They ask the trend out of the values given in the table. Okay? So I will spoon feed you, make your workload easier. Just remember these trends that I'm going to write over here. So the radii is actually boron is the smallest, then will be the gallium, then will be your aluminium, then it will be your indium, and then it will be your thallium. So can you see that there is one exception over here? What should be the general case? The general case should be, as I move down the group, the radii must increase. But what is happening? There is actually an anomaly here. There is an exception over here, that gallium's radius is actually smaller than aluminium. Why? Because gallium has introduce d orbitals in it, and due to the d orbitals are poor shielders. Poor shielders. What does it mean? Poor shielders. What does it mean? It means that the d orbitals over here will actually contract the size of the atom. Okay, you just have to understand this part. They are poor shielders, hence the radius actually decreases. So this is actually the trend followed. So this is the exception. I'm going to draw a circle around all the exceptions so that when you get the notes, you will know automatically this is the exception there. Okay, this is understood by all. Now let us move forward to the next. This is a graphically I have shown here, not important, only this trend is important. Now next is ionization enthalpy. I just told you what happens as we go down, the size increases. If the size is increasing, what should actually happen? The general trend should be that the ionization energy must decrease, right? Ionization energy must decrease because the size is increasing. But what is the trend of ionization energy? This doesn't happen. What actually happens? I'm going to draw a basic graph for you guys. Remember this graph. Okay? Graph is just for your reference. What is the graph? Here I'm drawing a W. Here it is a W, then W, then W and W. Right? So what I've drawn over here, bacha, I've drawn a crooked W over here just like this. Okay? Now write down the name of the elements on each of the points. So for example, I wrote B over here. This is boron. This is aluminium. This is gallium. This is indium. And this is thallium. What I'm drawing, I'm giving you a way to remember what is the ionization trend. So what is the ionization energy trend? It is actually boron. Can you see it is on the top? So boron will have the highest ionization energy. Then which one is the top? Thallium. So then thallium will have the highest ionization energy. Then can you see it is gallium? Then gallium will have the ionization energy. Then can you see aluminium? Then the aluminium will come, and then at the end it will be indium. So this is actually the ionization energy trend that is followed. Boron has the highest, then thallium, then gallium. Why is it happening? Because in thallium, for the first time, f orbitals are introduced, and due to the introduction of f orbitals, what happens? There are poor shielders, hence the size actually decreases. When the size is decreasing, the ionization energy increases. Now in gallium, d orbitals are introduced. Again, F and D both are poor shielders. Poor shielders, right? Poor shielders do what? You just have to remember one thing. Due to the poor shielding, the size decreases. Hence, ionization energy decreases. And if you have to compare between the shielding effect of F and D orbitals, then remember that D are better shielders than F. Okay? D are better shielders than F. Remember this thing. We actually study this thing in D and F block elements, which I've already taught you. If you haven't seen that lecture, you can go and see. I've explained the shielding effect extremely beautifully there. Right now, just remember this thing, and hence the other trend is this. So just follow how to remember the ionization trend. Remember this graph. Very easy to draw a crooked W, right? For example, if you hit the W, it will take this shape, and hence the ionization energy followed trend is this. Remember this trend. Very, very important, right? And the next thing that you should know about ionization energy, let us compare, this is group number 13, right? Let us compare the ionization energy of, okay, sorry, I will do here. I will again make a tiny box over here. Now I will tell you the ionization energy, one of which one is more? Ionization energy, one of group 2 is more or group 13 is more? Who can tell me? Who can tell me between group 2 and group 13 whose ionization energy will be more? Who can tell me? Group 2 belong to the S block elements. This is the P block elements. What actually happens? What actually happens? Who can tell me? I'm looking at the chat box. Please answer me. Sarath, the size order. Sarath is confused about the ionization energy and the size order. The size order I taught you is this one. ठीक है, is this only. Do not get confused. The size order will remain this. But in the ionization energy, this trend will be followed. But to understand why thallium has a lower ionization, higher ionization energy than gallium, then understand because thallium has f orbitals in it. Hence, its ionization energy is higher. Just to make you understand. Now, between the ionization energy of group 2 and group 13, who will have a higher ionization energy? Group 2, what is the electronic configuration? It is Ns2, right? Ns2. For group 13, the electronic configuration is Ns2, Np1, right? This is Ns2, Np1 is the electronic configuration of group 13, right? From where is it easier to take out the electron? It is easier to take out the electron from here, right? Because this is a stable configuration. Can everybody see? Ns2 is a stable noble gas configuration. Very difficult to take out the electron from here. So ionization energy of group 2 will be much more than group 13. Is this thing clear to you guys? Looking at their electronic configuration. Is this thing clear to everybody? Is this thing? Yes, group 2 will have a higher ionization energy. Very important points. So I've mentioned all the points over here. Next is oxidation state. What happens to the oxidation state? Again, to understand, you must know the electronic configuration. I'm again going to draw here. The electronic configuration is Ns2 and Np1, right? This is the electronic configuration, Ns2, Np1, right? Now, what can happen for showing the oxidation state? How many oxidation state can it show? If it gains some energy, what can be the other configuration? For example, I gave some energy to it. So, at the higher energy, what can happen? At the higher energy, this electron can go and jump over here, right? And it will get a configuration like this, Ns1 and Np2. At higher energy, it will get this configuration. So now tell me how many oxidation states are possible. Number first is कि one electron is lost from here, right? So one possible oxidation state is +1, right? The next possible is all the 3 electrons are lost, right? So the next possible configuration is +3. So +1 and +3 oxidation states are the possible oxidation states for this particular thing, right? So boron shows how many oxidation state, bacha? Boron just show +3 oxidation state. Remember this thing. Boron never shows +1, it only shows +3. Aluminium also shows +3 oxidation state and +1 very rarely. Remember this thing. Similarly, gallium, indium and thallium, they show +1 and +3, both kinds of oxidation states. So remember this thing, boron only +3, aluminium mostly shows +3, sometimes very rarely shows +1, right? Gallium, indium, thallium shows both +3 and +1. Now let us look at this table once again. What happens as we move down the group? As we move down the group, what happens, bacha? The stability of +3, I'm writing it here. As I move down the group, stability of +3 actually decreases and +1 actually increases. Remember this thing. What happens as we go down the group? The stability of +3 oxidation state decreases and +1 oxidation state increases. Why does it happen? It happens due to an effect which is called the inert pair effect. What does this mean? Inert pair means due to introduction of d and f orbitals. What happens? Whenever d and f orbitals come in picture, what actually happens? They do not let the s orbital participate in bonding. Okay? Do not let s orbital participate in bonding. Okay? What am I saying? For example, here the electronic configuration was Ns2 Np1. Okay? If one electron goes from here, its electronic configuration is +1. Now, as I move down the group, the s orbitals are held tightly. As you move down the group, the s orbitals are held tightly due to the inert pair effect, due to the introduction of DNF orbitals. Hence, s orbitals do not participate in bonding, and hence, as you go down the group, +1 oxidation state is the most stable oxidation state. Why? Due to the introduction of DNF orbitals, they do not let the s orbital participate in bonding. Hence, +1 is the most stable oxidation state. Everybody understood this? Everybody understood this? ठीक है? ठीक है? Very rarely बच्चा aluminum will show +1 oxidation state. Very, very rarely. ठीक है? Now let's talk about the stability of oxidation state. Hence, can I write the stability order over here? I am writing the stability order. What stability order will it follow? So here it will follow, for example, aluminium +3 will be the most stable, right? And then it will be gallium +3, and then it will be indium +3, and then it will be thallium +3. So this is the stability order of +3 oxidation state. ठीक है? Similarly, for the +1 it will be ulta. The aluminium +1 will be the least stable, then it will be gallium +1, then the indium +1, and then it will be thallium +1 are the most stable oxidation state. ठीक है? Everybody understood this order? Everybody understood this order? Next thing that you should know. So as I told you, I again told you कि in thallium what happens? In thallium, the +1 is more stable than +3. Everybody understood this? In thallium, +1 oxidation state is more stable than +3. Then what happens, bacha? If any compound, if thallium +3 is given to you, if thallium +3 is given to you in question, and now I know that thallium +3, ma'am, is not even stable. It will want to convert. It will want to convert into thallium +1, right? So what it is doing? It is itself getting reduced, right? It is getting reduced from +3 to +1. Hence, it is acting. Hence, thallium +3 act as a very, very good oxidizing agent. So because it is itself getting reduced, hence the property, hence the compound which itself gets reduced, it is called the oxidizing agent. Hence, thallium +3 compounds are extremely good oxidizing agents for this reason. Everybody understood this? है ना? The next thing that you should know about oxidation states is what, bacha? I told you it shows +1 and +3 oxidation state. The other thing that you should know about, because in +3 oxidation state, what is happening? In +3 oxidation state, you have to remove 3 electrons, right? So removal of 3 electrons require 3 ionization energy. Ionization energy 1, ionization energy 2, ionization energy 3, which is very much, right? Lot of ionization energy. Hence, +3 oxidation state compounds are usually not ionic but covalent compounds. Similarly, +1 oxidation state compounds are usually ionic compounds. And why is the case? Because to take out 1 electron is easier, right? It is easy because I just need 1 ionization energy. But for +3, for showing +3 oxidation state, 3 ionization energy is too much energy I need to give. Hence, those compounds are not ionic. They are only covalent compounds. Everybody understood this? Everybody understood this? ठीक है? And another thing that I want to tell you is, कि boron in +3 oxidation state is usually covalent, right? While aluminium in +3 oxidation state can be ionic. We have seen aluminium chloride compounds. They can be ionic. Okay? Not always ionic, but can be. Can be a little ionic. Okay? But mostly, if the question comes for you, you have to write the +3 will show covalent compounds, but +1 will show ionic compounds. Okay? This is just a trivia that I'm telling you. It's not because we have seen aluminium plus 3 ions, right? You've seen aluminium plus 3 ions in solutions. So you should actually speak, ma'am, those aluminium plus 3 to are ionic compounds. So it can happen. But with aluminium, with boron, they're always and always covalent compound. Everybody understood this? Everybody understood this? ठीक है. ठीक है. Next, this is a problem in your NCERT. I've taken each and everything from your NCERT. We're not leaving even single thing. The question is, standard electrode potential values are given to you. That is, your E naught values are given. E naught for aluminium plus 3. Aluminium plus 3 to aluminium is given to you minus 1.66 volt, right? So what is happening? When you convert aluminium plus 3 to aluminium plus 1, what are you doing? You're converting from plus 3 to plus 1. The E naught potential is negative. Okay? Is negative. The other one that is given to you, the E naught potential for your thallium. Thallium plus 3 to thallium is again given to you, which is actually a positive quantity. Plus 1.26 volt is given to you. And it is asking you predict about the formation of M plus 3 ion in solution and compare the electropositive character of the two metals. So it is asking where M plus 3 ion will be made easily. Where will it be made? So whenever bacha E naught value is positive, it means that the reaction will be spontaneous. Remember this thing, it will be a spontaneous reaction. So where is the value positive? So when I am converting thallium plus 3 to thallium, the E naught is positive. Hence I know what? Hence I know that thallium plus 1 ions is stable, right? Thallium plus 1 ion is actually stable, but it is asking about the formation of M plus 3 ion, है ना? So M plus 3 is aluminium plus 3 ions will be formed easily, because their reduction is very difficult. When I'm trying to reduce plus 3 to plus 1, minus value is coming. Minus is not spontaneous reaction. Hence, it will not happen. It will not happen. So, aluminium plus 3 will be what, bacha? Aluminium plus 3 will be formed more easily. Okay? M plus 3 ion formation in solution will be easier for aluminium plus 3. Everybody understood this? Hence, aluminium plus 3 means what? It is more electropositive. So, I can say that which is more electropositive? Aluminium plus 3 is more electropositive. Electropositive, right? Okay? What is electropositivity? Again, where the formation of positive ions is easier. So, because plus 3 ions is easier with aluminium, it is more electropositive. It is easier to form because its reduction is extremely difficult. Hence, it will not happen. Is this thing clear to everybody? Is this thing clear to everybody? With the coordination chemistry notes you need, it is linked in the Telegram channel below. You will find it from there. I have sent it to the Telegram channel for the coordination chemistry. Next, AIPMK 2009 question. The stability of plus 1 oxidation state among aluminium, gallium, indium and thallium increases in the sequence. What is the answer to this question? Let me know in the chat box. Is it option A, B, C or D? What happens? Who can answer this? AIPMT 2009 question. Again repeated recently again. Who can answer this question? I am looking at the chat box. Please let me know. Please, please, please. Let me know. Let me know. And also please like the session if you've just joined it. If you're watching it, if you like it, please like the session because that helps me. Because if I'm helping you, it's only fair that you help me back, right? So just like the session because it helps other students to discover this more. Correct? Chalo, next. A, somebody is saying A. So thallium, indium, gallium, and very, very good. The answer is actually A. Stability of plus 1 increases in this order. Correct. Absolutely correct. The first one to actually answer A was who? Venki. Then Pradeepa, then Jyoti, then Sabrina. But Pavish, you're wrong. The answer is actually for plus 1 oxidation state. I just told you. As you go down the group, the stability of +1 increases. So the down the group, thallium is present, so it will be the most stable with +1 oxidation state. Correct. Now let's see the electronegativity order. Very important order once again. How to remember this order? Okay, just remember this thing. The electronegativity is actually boron is the most electronegative, right? So just most electronegative, and after that just begin writing ulta order. Just begin writing the ulta order. What is the ulta order? Now it will come thallium, then it will be indium, then it will be gallium, and then it will be aluminium. So can you see this entire order I've written ulta over here? So boron is the most electronegative element. What is the meaning of electronegative element? That it has the most tendency to attract electrons to itself. Why? Because it is smaller in size than the thallium, indium, gallium and aluminum. And whatever metal is actually the most electronegative is actually a non-metal, right? Most electronegative element will always be a non-metal, and most, so this becomes, so because aluminium is least electronegative, which means what? It is the most electropositive element, right? So aluminum is the most electropositive element. It is the most metallic element, hence. Correct? So this is the only order that you need to know about electronegativity. What is the definition? Nobody asked you, but it's just that which can attract electrons towards itself most easily is called the most electronegative element. Okay? Now next we're again discussing about the metallic and the non-metallic character. So the metallic character, bacha, metallic character depends upon the electropositive character. Remember this. Electropositive character depends upon. So you should also know the electropositivity order, which is the reverse of electronegativity order, right? Because boron was the most electronegative. Hence, it will be the least electropositive. So, electropositive order is boron, then thallium, then indium, then gallium, and then aluminium is the most electropositive element. Hence, it is the most metallic element. Can you see among these metals? Hence, aluminium is the most metallic element. Okay? So this is the order. So this order that we just wrote here, bacha, what happened? 1 second. Yes. So this order that I wrote here is the electropositivity order plus the metallic order. If anybody asks you what is the metallic order, this is also the metallic order. Aluminum is the most metallic, then gallium, indium, thallium, boron is the non-metal once again. So you should know among these only and only boron is the non-metal, all others are metals, and among these aluminium is the most metallic element. Correct? Everybody understood this? Aluminium is the most metallic element. Please understand these things. ठीक है? Which symbol are you confused with, Pavish? ठीक है? Melting point and boiling point we're going to talk about. I'm going to explain to you a very basic thing because we're going to learn about each and every group, right? So in each and every group we're going to discuss their boiling points, melting point order, right? So right now we're just discussing group 13. So what is the boiling point order followed for group 13 and group 14? So what the boiling point depends upon mostly the size. Boiling point order depends upon the size. As the size increases, what happens? Their van der Waals forces, the van der Waals forces also increases, right? So as the force will increase, the boiling point will also increase. So for the boiling point, a similar trend will be followed, that as the size increases, the boiling point also increases, correct? But for melting point order, you can never predict. You can never predict melting point order of any group. Why? Because melting point is actually dependent upon the crystal lattice. Crystal lattice. Remember this thing. Okay? So whatever is the arrangement of the crystal lattice, it will determine its melting point. So you cannot just look at a group and just let me know ki, okay, this melting point will be highest, this will be lowest. No, you have to study it chemically. Only then, after studying its crystal structure, we can know its melting point. So the melting point or trend will never be a normal trend. ठीक है. So I'm going to write all the melting point. So the boiling point order will be, number first, the easiest. The boiling point order will be what? Boron will be the highest, then it will be the aluminium, gallium, indium and thallium. Okay, here a reverse order is followed for the boiling point. Just remember this thing. Okay, reverse order is followed for the boiling point. Then for the melting point, bacha, what happens? The highest melting point is of boron. Okay, then it is of aluminium. Then it is of your thallium, indium and gallium. Then it is thallium, indium and gallium. So can you see there's an exception that begins from thallium? Can you see this exception? So this is the boiling point order. Here boiling point is also a certain exception, I know. In melting point, the boron has the highest melting point. Why? Because boron is made up of icosahedral units. Okay? Its crystal lattice is made up of icosahedral units, which makes its melting point extremely high. Okay? Highest melting point due to its unique crystal structure. Everybody understood this? Everybody understood? The other thing that you should know is the gallium metal over here, because it has a low, can you see it has a low melting point, it also has a low boiling point, and due to that this gallium metal is used in a study of various temperature dependent phenomena. Okay? So gallium is used in various temperature dependent phenomena due to its special low melting point and boiling point property. Okay? Next, melting point, boiling point we've discussed. Next is density. Density, what is the formula for density? It is mass upon volume, right? So as the mass increases, density also increases. But if the volume increases, the density will decrease. This you know, right? So mass upon volume is a density order. Hence, what is the trend? The trend is simple: boron, aluminium, gallium, indium and thallium. This is the density order. Very simple. There is no exception in the density order. Okay, everybody understood this? Now let's move on to the very next thing. Let me take out the chart box. Okay, decreases down the group. Correct. Next is group 13, physical properties. So I told you that boron has a very unique icosahedral crystal structure, very high melting point, and due to that it is extremely hard. The boron is extremely hard, black colored solid, and it exists in many allotropes. What are allotropes, you'll ask me? So whenever allotrope word comes, just remember about carbon. You know that carbon exists at so many allotropes. Carbon exists at graphite, as a diamond, as a Buckminster fullerene, right? So there are so many physical forms of carbon. Even though graphite, carbon, are all made up of just one element, that is carbon, right? But still, their physical structure, the arrangement of their atoms is different, due to which their physical properties changes. So those are called allotropes. Allotropes are changes in physical properties. Similarly, boron also exists in so many allotropic forms. For example, its structure changes, hence its physical properties will also changes. It exists in many allotropic forms and it has an unusually high melting point, which I just discussed. Okay, rest of the metals, rest of the elements here are metals. I told you only boron here is a non-metal, rest are metals. And what is the property of metal? That they have low melting point and high electrical conductivity, because they're metals, so they will have a high conductivity, but they have a low melting point. And they are soft metals. Because they are soft metals, hence they have a low melting point. Okay? Everybody understood this thing? Next is chemical properties of compounds in trivalent state. What is trivalent state? I just told you. Group 13 shows +3 oxidation state, which is called a trivalent state. Now, whenever compounds is present in +3 state, what will be their chemical properties? We are going to discuss here. So, for example, right now I am writing a compound called BCl3 in front of you. Can everybody see BCl3? Now, what will be the diagram of BCl3? I can form BCl3 like this. This is boron and 3 chlorines are attached to it. 1 chlorine, 2 chlorine and 3 chlorine. Now, count the number of electrons this boron has. How many electrons does this compound have? This compound have 1 electron, 2 electron, 3 electron, 4 electron, 5 electron and 6 electron. Can you see? This boron in a +3 oxidation state is actually a 6 electron species. है ना? 6 electron species. BCl3 here, boron is in +3 oxidation state and here it is a 6 electron species. Is its octet complete? No. It has a incomplete octet. Can everybody see? It has a incomplete octet. It means what? It means what? That this is actually electron deficient, right? Everybody agrees with this point. This is actually electron deficient because it only has 6 electrons. It's electron deficient. Its octet is not complete. And whichever species are electron deficient, which means it can attract electrons in itself. So what species are electron deficient are actually called what? They are called Lewis acids. Remember this. Because they are electron deficient, hence they act as very good Lewis acids. Remember this thing. Okay? Now I'm going to write the Lewis acidity trend over here. So what is the Lewis acidity order? Lewis acidity, very, very important point. Lewis acidity order. What is the order that is followed? Okay? The order followed, bacha, is boron is the most Lewis acidic. Then it will be your aluminium, then your gallium, then your indium, and then your thallium. Okay? This is the Lewis acidity order. Boron is the highest Lewis acid. Means it will attract electrons more towards itself, right? So boron is the most Lewis acidic, then aluminium, gallium, indium, and thallium. Now you know why they act as Lewis acid. Correct? You understood this point? Everybody understood this point? Okay? The next thing that you should know before this, okay, I will draw here only I will draw. Acha, next page I can draw. So I will explain to you later on what do I mean by here. Now, because I told that BCl3 is actually a Lewis acid. Okay? If BCl3 is a Lewis acid, it means that it can react with a base. Because this is a Lewis acid, it can react with the base. For example, Lewis base is what? Lewis base is anything which is electron rich. Can you see this ammonia? This NH3 has lone pair of electrons and hence it can donate lone pair of electrons to this structure, right? And it can form an adduct. Okay? So BCl3 here had a planar structure. Everybody saw that structure? What kind of structure is this? This is a planar structure where boron is sp2 hybridized, right? Boron is sp2 hybridized, is a planar structure. So when it forms an adduct, it actually forms a tetrahedral structure like this. This is boron, this is Cl3, 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 Cl, 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 and here it will be your ammonia giving its electron to this. So an adduct like this is formed. So a tetrahedral structure is formed with your BCl3. Lewis acid and Lewis base act together, react to form a tetrahedral structure. Everybody understood this point? Okay? Now, bacha, BCl3. As I told you, what is the property of boron? Boron has no d orbitals. Remember this thing. Boron has no d orbitals. Hence, the maximum number of bonds it can form is 4. Can you see it has formed 4 bonds? So this is the maximum number of bonds that it can form. But in aluminium, what happens? Now you will talk about, ma'am, in AlCl3 also, it is electron deficient, right? It is again, I'm writing it here, it is again electron deficient, right? Why? Because this again has only 6 electrons in itself. So what does AlCl3 do? AlCl3, because it is electron deficient, hence it forms a dimer species just like this. Can you see that AlCl3 forms a dimer with another AlCl3 and forms a dimer just like this. But your BCl3, your boron, can never form a dimer. I am writing it here. Okay? Boron never forms dimer. Why? Because boron does not have d orbitals, hence it cannot expand its valency beyond 4, but aluminium has vacant d orbitals, hence it can expand the valency up to 6, hence it can form a dimer. So aluminium AlCl3 again is electron deficient. So to reduce its electron deficiency, it actually forms a dimer like this. So dimer is no more electron deficient, all its electronics, its octet is complete, hence it forms a stable dimer species. But in boron, this dimer is not possible. Understood this? So in trivalent state, I taught you so many things. In trivalence, because the 13th group is trivalent, it acts as a Lewis acid. Because it acts as a Lewis acid, I told you the Lewis acidity trend. Boron is the most Lewis acid. The next thing is, to complete its octet, only aluminium can form a dimer. Boron cannot form a dimer. Okay, everybody understood this? Can we move on to the next point? Correct? The next point is the nature of compounds. What do I mean by nature of compounds? Again, the boron. I'm talking about boron over here. What are the properties of boron? I'm writing here. Boron actually has a small size. Remember this thing. Boron actually has a small size. What is the second thing? The second thing is that it has high electronegativity, right? It has high ionization energy. And the fourth thing is it has no d orbitals. Okay? So due to all these things, what happens? That the compounds of boron and the compounds of rest of the elements are actually different, because boron shows, due to these 4 properties, it shows anomalous properties. Okay? Now the nature of compounds I'm writing here, over here. Boron bacha actually always form covalent compounds. What kind of compounds? The covalent compounds will be formed. In aluminium, again, covalent compounds will be formed, and rarely ionic also can be formed. Okay? I'm writing it over here. The next thing that you should know. The next thing, what are the covalent compounds of aluminium? The covalent compounds are, for example, AlCl3, AlBr3, for example, AlI3. These are all covalent compounds. Okay? All these chlorides, I'm talking about trivalent compounds. These are all covalent compounds. What are the ionic? The ionic trichloride is just AlF3. It is the only ionic. Why is it ionic? This is explained by Fayon's rule. You read it in chemical bonding. Everybody understands the Fayon's rule, that when the anion is smaller, the ionic character increases. Can you see? Fluorine is the smallest. So AlF3 is actually an ionic compound. Okay? Similarly, I'm talking about next, gallium and indium. What happens with gallium and indium? So the gallium chloride, GaCl3, and your indium chloride once again. These are again, bacha, your covalent. Okay? These are covalent compounds. Okay? All these things you should remember. So these are the nature of compounds that you should know. The only ionic compound we have discussed in trivalent state is actually AlF3. Rest all are covalent. Boron always form covalent compounds. Aluminium sometimes form ionic, which I told you, and the rest of the compounds are again covalent compounds. Everybody understood this? Okay? Nature of compounds we have discussed. Now the chemical properties of compounds in trivalent state. What are the chemical properties in trivalent state? Trivalent is in +3 oxidation state. What happens? They are covalent and are hydrolyzed in water. Covalent compounds I told you, right? Aluminium chloride, aluminium bromide, gallium chloride, indium chloride. All these are what? All these are covalent compounds. And these covalent compounds are hydrolyzed in water. When you put them in water, they get hydrolyzed. Very, very important. Okay? For example, any metal, M here represents any element from group 13. Could be boron, could be indium. Okay? So MCl3 on hydrolysis in water forms a tetrahedral MOH minus species. Who forms MOH minus species? Only and only boron. So when you put boron in water, it will form a boron hydroxide 4 minus species. But when you put aluminium chloride in acidified aqueous solution, it actually forms a octahedral species. Can you see AlH2O6? So it actually forms a octahedral species. So boron forms a tetrahedral species. What kind of species this is? This is a tetrahedral species. But your aluminium forms a octahedral species in water. Your boron forms a tetrahedral species because boron cannot expand covalency. Covalency is what? Covalency means number of bonds. So the maximum number of bonds or the maximum number of covalency boron shows is 4, but aluminium, because it has vacant d orbitals, it can expand its valency to actually 6, can form a octahedral in water. Very, very important point. Extremely, extremely important point. Okay? Now we're talking about reactivity with air. I've discussed the reactivity with water. Now we're talking about reactivity with air. So in air, what are the maximum elements present? What are the elements present in most abundance? In air, the elements present in most abundance are oxygen and nitrogen, right? Everybody is familiar with that. So oxygen and nitrogen forms the most compounds with this. Okay? So elements react with oxygen at moderate temperature to form oxide and with nitrogen at higher temperature to form nitrides. Why? Because the bonding in nitrogen is nitrogen, N2 molecule. The N2 molecule has a triple bond, while the O2 molecule actually has a double bond, right? So which is easier to break? The double bond is easier to break, hence it forms at moderate temperature, but because triple bond is harder to break, hence nitrides are formed at higher temperature. So what happens? Oxides, what kind of oxides are formed? The oxides are formed in M2O3, right? And the nitrides are formed as Mn compounds. Remember this thing. This is the molecular formula. When boron reacts with oxygen, it forms B2O3. When aluminium reacts with oxygen, it forms Al2O3, right? And similarly, when boron reacts with nitrogen, it forms Bn. When aluminum reacts with hydrogen, it forms Aln. So here M represents any element that is over there. So this is the general formula of the compound. I want to tell you another interesting fact, which is only amorphous boron reacts with oxygen. Only amorphous boron reacts with oxygen. Okay? Your crystalline boron do not react with oxygen. Remember this thing. Okay? Your crystalline is unreactive towards oxygen. Okay? And with boron, this is the one thing that you should know. The other thing that you should know, that the boron on reaction with nitrogen forms a boron nitride. I told you about boron nitride, which is used in the bulletproof vest, right? And this boron nitride has a similar structure to bacha graphite. Has a similar structure to graphite. Hence, it is also called inorganic graphite. So your Bn is isostructural to graphite. Hence, it is called inorganic graphite. Very, very important point, can be asked in the questions. So abhi tak what have we discussed? That when I react these elements, boron, aluminum, gallium, indium, thallium with oxygen, what kind of compounds are formed? The general formula will be M2O3 and Mn, right? And in boron, only amorphous boron is reactive with oxygen. Crystalline boron does not react with oxygen. ठीक है? The next thing you should know about aluminium. Let's discuss. Acha, here it is not present. So let's discuss aluminium again. So bacha, aluminium actually forms a protective oxide layer on reaction with oxygen. What happens? Aluminium in presence of air forms a protective oxide layer outside it, and hence when I try to react it with more oxygen, there is no reaction happening. ठीक है? So what I'm saying कि Al2O3, aluminium forms a protective oxide layer. ठीक है? Due to which it is again unreactive, due to which it remains unreactive towards oxygen. Just remember this. But if I heat it, it can become reactive. Everybody understood this point? Everybody understood this point? ठीक है? ठीक है? चलो next. So I also want to tell you one more thing. I told you that every other oxide is formed in the formula M2O3. But with thallium, two kinds of oxide are formed. That is Tl2O3 as well as Tl2O. Why? Because thallium is stable in +1 oxidation state also, remember? So that's why Tl2O is also formed with thallium. Otherwise, all other oxides will be, indium will be IN2O3, correct? But with thallium, we also get thallium 2 oxide. This can be the general formula as well, because thallium shows stable +1 oxidation states. Okay, everybody understood this point? Reactivity towards air we've discussed. And I also told you that boron nitride has a graphite-like structure. That's why it's called the inorganic graphite, because it is a layered solid, inorganic graphite, white solid. It also is an insulator and it is very, very hard. And you can convert the graphite form of boron nitride to the diamond form by increasing the temperature and pressure. Okay? So this is a basic structure of boron nitride. The next is reactivity towards air. The other thing that you should know, after I've made the M2O3 oxide, now I'm reacting the oxide. Firstly, previously I was reacting chlorides with water. Here I'm reacting oxides with water, and I will get a structure just like this, MOH, right? MOH3. So hydroxides I can get if I react oxides with water. When I'm reacting oxides with water, I'm getting hydroxides. Now we're going to talk about the acidic nature and the basic nature of oxides. Very important question. So I'm going to write down all the oxides over here. All the oxides here are, I'll start with B2O3, and here below that I will write the hydroxide of boron as well, BOH3. Here I will write Al2O3, and here I will also write the hydroxide of aluminum, AlOH whole thrice. Right? Here I will write gallium, Ga2O3, and the hydroxide of gallium. Okay? Here I will write indium, In2O3, and the hydroxide of indium. Right? And here I can write thallium. The stable is +1 oxidation state, so oxide will be Tl2O, and here it will be TlOH again. Okay? Here it will be TlOH. Now let's discuss the acidity and the basicity trend. So what happens, as I told you, here all are metals. This is a non-metal. Boron is a non-metal, and the oxides of non-metals are always acidic oxides, right? So this oxide, bacha, is oxide as well as the hydroxide is acidic in nature. Remember this. Now with aluminium and gallium, both the oxides and the hydroxides are actually amphoteric in nature. Amphoteric. What is meant by amphoteric? It means it reacts both with acids and with the base. It means, okay, amphoteric means it reacts both with the acid and the base. Similarly, your indium and the thallium oxide, let's talk about that. Your indium is actually a basic oxide, correct? And your thallium oxide as well as the hydroxide is actually highly basic oxide. Remember these points, very, very important. Can everybody see on the hydroxide and oxides? I just discussed with you very, very important thing. So this is how they react with the air, and this is the acidity-basicity order asked every year in exam. Very, very important trend. Please look at this trend. I will just give you a little side over here. Okay? Everybody can copy this down. Otherwise, you will get the notes on the Telegram channel. Don't worry about it. Just understand this. Now, reactivity towards here we discussed. I think we've discussed all the reactivities right now. Let's now study the reactivity with acids and alkalis. So, what happens? Boron trioxides, okay, B2O3 is acidic. I just told you, and reacts because it is an acidic oxide. React with bases. So it will react with a basic or a metallic oxide to form metal borates. Remember this thing, okay? So acidic and basic oxides will react together to form metal borates. The next thing is boron does not react with acids and alkalis even at moderate temperature, okay? Boron does not react with acids and alkalis even at moderate temperature. So boron will not react with acid and alkali even at normal. Simple boron I'm talking about, not boron oxide. I'm talking about simple boron. It will not react with either the acid or the bases even at moderate temperature. Okay? Okay, everybody understood this? Everybody understood this? The other thing is, what I'm saying here, I'm saying that if I try to react boron with HCl, there will be no reaction. But if I try to react boron with the oxidizing acid, what is oxidizing acid? For example, in presence of concentrated HNO3 or your H2SO4, these are your oxidizing acids. So in the presence of this, it actually forms H3BO3, which is your orthoboric acid. It forms orthoboric acid or the boric acid in presence of this, while the all other elements, okay, all other elements, if I try to react from, for example, I'm writing E from aluminium to thallium. What happens? From elements from aluminium to thallium, if I try to react them with any acid, they will actually give out hydrogen gas. Okay? Aluminium, gallium, indium and thallium will react with the acid and give out hydrogen gas. Okay? Now if I try to react boron with alkali, there will be no reaction with aluminium and gallium. Okay? Now what happens? Now I try to react it with them with the base. Now if I try to react boron with the base, then what will happen? Even at increased temperature, there will be no reaction. Okay? Now if I try to react aluminium or even your gallium. Okay? Now if I try to react, one second, yes, aluminium or even your gallium with a base. I told you that aluminium and gallium are actually amphoteric compounds. What kinds of compounds are there? They are amphoteric. It means it reacts both with acid and with a base. When it reacts with the base, it actually again gives them hydrogen gas. Previously also I told you that all the elements from aluminium to thallium react with the acid to give out hydrogen gas. Okay? And aluminium and gallium also react with the base to give out the hydrogen gas. Okay? Rest of the elements, which is your indium or your thallium, what happens? These were already basic compounds because these are basic, not amphoteric. Hence, if I try to react them with a base, there will actually be a no reaction. Very, very important points I'm telling you over here. Extremely, extremely important points. Everybody understood this? Everybody, please let me know in the chat box. Understood, Sarath? Very good, Sarath. Very, very good. Understood. Extremely good. Extremely good. Next is, I'm going to tell you a little more thing about that. Aluminium dissolves in mineral acid. Mineral acid is what? Which gives away H+. Any acid capable to give away H+ is called a mineral acid. For example, HCl, HNO3, whatever. Mineral acid and aqueous alkalis and thus show amphoteric character. Aluminium reacts both with acid and the base. Hence, it is amphoteric in nature. I just told you. For example, aluminium with HCl gives out hydrogen gas. Aluminium with a base again gives out hydrogen gas. But here, a complex is formed. Very, very important point once again. This is a NEET question. NEET question asks, कि when aluminum reacts with the base, what is the complex form? The complex form is NaAlOH4 minus. Remember this thing. ठीक है, concentrated nitric acid. Nitric acid is what? HNO3. But when you take concentrated HNO3, aluminum again becomes passive because it forms a protective outside oxide layer outside it. है ना? HNO3 is what? It is a very good oxidizing agent. Hence it does what? It forms a protective oxide layer outside aluminum. Hence aluminum will not show any further reaction because that Al2O3 layer outside aluminum is unreactive to acids as well as oxygen. Everybody understood this? Did everyone understood this part? With oxidizing agent, again it forms a protective oxide layer outside aluminum. Hence, it renders passive means what? It will not show any reaction further. Any reaction further. Understood? Very, very good. Now we're talking about again reactivity with halogens. So what happens with the react? Oh, I didn't discuss one trend now. I guess. Yes, I didn't discuss one trend. Let me go back. Reactivity towards air. So which of these elements is actually most reactive towards oxygen? There should be a trend, right? So the reactivity towards the trend, what should be the reactivity order? Trend of reactivity order. So what is the trend of reactivity order? It is bacha, boron is the least reactive with oxygen. Then is your aluminium, then gallium, then indium, and then thallium. What does this mean? Ki thallium is most reactive with oxygen. It means what? So you have to understand this thing by looking at their size. Oxygen is made up of O2, two oxygen big molecules. Oxygen is a bigger molecule. Hai? So bigger molecules form stable bonds with other bigger molecules, right? So as the size increases, the reactivity with oxygen will also increase. Always remember this thing. The reactivity order depends upon basically it will depend majorly on its size. Because oxygen is a bigger atom, hence it will form stable bonds with another bigger atom, hence those will be more reactive. So thallium, with thallium, oxygen is more reactive than indium, then gallium, then boron, then okay. So this is the reactivity order followed with this thing. Everybody understood? Okay. Now next, let's go back to the halogens. Reactivity towards halogens. I just need to see if I am discussing each and everything. Correct. So with halogens, again I told you, what kind of compounds will be formed? EX3. Trihalides compounds are most stable, right? Most form are the trihalide compound. And I just discussed with you, most of these trihalides will be covalent in nature. Why? Because taking out 3 electrons is extremely energy, requires so much energy, because I need to take out 3 electrons, I need 3 ionization energy, which is a lot of energy, but I require least energy. Hence with covalent, EX3 compounds majorly will be covalent compounds. Okay? For example, ECl3, EBr3, right, and EI3 will be your covalent compounds. Okay? And these covalent compounds are hydrolyzed with water. I just told you these are hydrolyzed by water. We just discussed this, right? So I just told you that these all the trihalides hydrolyze with water and forms what? With boron it forms a BOH4 minus like structure, right? With a tetrahedral structure. But with aluminium, it actually forms a AlH2O6 kind of structure, which was your octahedral structure. We just discussed all these things, right? With boron, it forms a tetrahedral structure. With aluminium, it forms an octahedral structure, right? We discussed all these things, correct? And I also told you that all these trihalides are electron deficient, hence they act as a very good Lewis acid. Hannah, I told you all of these things. So let's discuss about other things. Which of these halides are covalent? So all the boron trihalides will always be covalent halides. I'm again telling you. Which will be ionic? The ionic will be F3. All the fluorides, aluminium fluoride, gallium fluoride, ठीक है, gallium fluoride, indium fluoride and your thallium fluoride will all be ionic fluorides, all be ionic. Only TLF is formed because thallium is stable in +1 oxidation state. Correct? Correct. Everybody understood this? Now let's discuss their Lewis acidity order. Lewis acidity order, right? Let's discuss their Lewis acidity order. As I discussed, all these trihalides are what? Electron deficient. Why? Because these are just 6 electron species, right? Because these are electron deficient, hence they will show Lewis acidic character. What is that Lewis acidic character? What will be the trend followed? So boron trihalide will be the most Lewis acidic, then it will be your aluminium trihalide, then it will be your gallium trihalide, then it will be your indium trihalide, and the least will be your thallium halide. Okay? So this is the Lewis acidity order. Now let's not write thallium over here, till indium we can write. Now if I'm gonna change the halide and keep the other things same. For example, bacha, Bi3 will be the most Lewis acidic, then your BBr3, then your BCl3, then your BF3. What is meant by this? Your boron iodide, boron triiodide will be the most Lewis acidic iodide. Halide. Why is the case? What is meant by Lewis acidic character? So, bacha, the Bi3, in Bi3, what? So, let's talk about boron trifluoride first. One second. La 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 la. Hi, Sarat. Sarat is replying too much to me. I think Sarat is studying. What is happened to the rest of the people? Are you not studying? Are you not studying? Why am I not getting too many messages? Why are you not asking me any questions? ठीक है. Now this we have discussed. The other thing that I was going to tell you, why BF3 is the least Lewis acidic. What is meant by Lewis acid? For example, this is the BF3 molecule, right? This is the BF3 molecule. Now, both boron and both fluorine only has p orbitals. Everybody can know that, है ना? So, because both of them only has p orbital, because these are both first element of each group. Both boron and fluorine only have p orbitals in that. Hence, what can happen? Because fluorine, bacha, is electron rich, right? Fluorine atom has so many valence electron. It is actually electron rich atom, right? It is an electron rich element. What it can do? It can do back bonding with boron. What it is doing? It is doing back bonding with boron and hence giving electrons to boron. है ना? So what is happening here? P pi, back bonding. P pi, back bonding is actually happening with BF3 molecule. So therefore, the fluorine is already giving electrons to boron, and boron was what? Electron deficient. So that electron deficiency is getting cured by the fluorine. So hence, it is no longer electron deficient, right? Because fluorine is giving its electrons to the boron. So this boron is now no longer electron deficient. Hence, this is the least Lewis acid. What is the condition for Lewis acidity? That it should be an electron deficient molecule. But here the electron deficiency is getting reduced by the fluorine atom due to the p pi back bonding. Hence, it is the least Lewis acidic. But what happens with Bi3? The iodine is a very big molecule, and in Bi3, what kind of bonding will be there? It will be p pi d pi back bonding, right? So the back bonding. So the back bonding present here will be the p pi d pi back bonding, which is least stable. It cannot effectively donate its electron to boron. Hence, the boron here is the most electron deficient species. Hence, it is the most Lewis acidic in nature. So, this is the trend followed for Lewis acidity when we're talking about trihalides. Is this thing clear to everybody? ठीक है? Is this thing clear to everybody? ठीक है? Now, next, Now next, reactivity towards halogen. This is a question given in NCERT. Can everybody see the question? The question is, white fumes appear around the bottle of anhydrous Cl. You've taken a bottle of anhydrous Cl3. Anhydrous means what? It has no water content in it. Give reason. And what happens on that anhydrous Cl3? White fumes are seen around the bottle. Why? Because AlCl3 will react with the atmospheric water. The water that is present in the atmosphere, the moisture in water will react with that, and it will form, bacha, what? It will form a AlOH6 kind of molecule, right? And this complex is actually what? This complex has a white color in it, okay? So, and it also liberates a HCl gas. It liberates HCl gas, and that's why moist HCl is white in color, and due to this HCl, the white color appears. Remember this thing. Due to this HCl, the white color appears. Okay? Now this is a 2010 NEET question, APMT question. The tendency of BF3, BCl3, BBr3 to behave as Lewis acid decreases in the sequence. What is the Lewis acidity sequence? See again, 2010 prelims question. I added 15 years of PYQs here. We're doing each and everything. We're not going to leave even one question behind. What can be the answer? Option A, option B, option C, or option D? Who can answer this? No, bacha, carbon do not have empty d orbital. Does not. No d orbitals in carbon. Carbon is the first element of the group. In second period, carbon belongs to the second period. Second period, there is no d orbital. D orbital starts from the third period. In third period, there is vacant d orbital. In the fourth period, there are filled d orbitals. Remember this thing, in the second period, there are no absent d orbitals. Okay? First answer by Pavish Yadav is B. He is saying that BBr3 will be the most Lewis acid, then BCl3, then BF3. Very, very good. This is the correct answer, Pavish. Then it was Abid, then Sarath, then Venki is giving the wrong answer. But no, Lewis acid. The most Lewis acidic character will be shown by BBr3. Why? Because in BF3, there is present of the most pipa-pipa back bonding, right? What is happening in BF3? In BF3, the F is donating its electron to boron. It is forming a pi-pi back bond. I just explained to you. Hence, the boron here is no longer electron deficient. Hence, it is the least Lewis acidic. It is the worst, weakest Lewis acid, while BBr3 is the strongest Lewis acid here. So the correct answer is B. Very, very good to all others. Okay, now AFMT 2000 question. Which compound is electron deficient? Who can answer this question? Which of these compounds? We have read only one of these compounds. Who can answer this? See again, very easy question. Which of these is electron deficient? Where the octet is not complete. Which of these can you see the octet or the duplet is not complete? In BeCl2 is what? Be, beryllium is a S block element. In beryllium Cl2, actually the duplet is complete. Okay? In BeCl2, you can again say, ki ma'am, here it is again an electron deficient compound. But here we take it as an exception because here the duplet we are considering for beryllium. But for boron, what is the answer? Answer will be B. So the correct answer is actually BCl3, correct. But here BeCl2 is given to confuse you. Remember this thing. Okay? Next. Anomalous property of boron. We've already discussed most of the things. I'm just going to orally tell you and not write anything on the board because now you know why boron properties are different from the rest of the elements. Why? Because first of all, boron has the smallest size, right? Because it just has two shells. It has the smallest size. It has the highest electronegativity. It has the highest ionization energy. And it has no d orbitals. Due to these four reasons, boron actually shows anomalous properties, different properties. What are those properties? Number first, it cannot form maximum covalency shown by boron. Maximum covalency shown by boron is just 4. Covalency means what? Covalency means maximum number of bonds. Covalency means number of bonds. So the maximum bonds that boron can form is 4. Why? Because it has no d orbitals. While the other elements, for example, the aluminium can form 6 bonds. It can form a octahedral structure as well. But boron can maximum form a tetrahedral structure. That is it. Aluminium again can form a dimer, right? For example, BCl3 is an electron deficient molecule. It only has 6 electron species, but it cannot form a dimer. But your AlCl3, which is again an electron deficient species, it actually forms a dimer just like this, right? So this dimer formation is possible only when, because the aluminium has d orbitals, hence it can expand its octet and it can form more than, it can form 6 bonds as well, but boron cannot do that. So boron can never form a dimer, but aluminium can form a dimer. Boron can form maximum 4 bonds, aluminium can form maximum 6 or octahedral structure, correct? So these are some of the properties that you should understand. Everybody understood this? Everybody understood these points. So till here we have completed the boron that is given in your course. But in your group 13, the compounds of boron, the compounds of aluminium are not in your reduced syllabus and will not come in NEET 2024. But I'm going to teach you certain structures which are important. Why? Because in your course, what it is given that reactions with hydrogen, oxygen and halogens are there. Hence, the structures related to that, their preparation, their properties and their preparation properties will not be asked, right? But the structures can be asked because it was asked even in JEE exam, है ना? Because NEET follows the pattern of JEE, just mark my words for that. So please understand few of the structures that I'm going to tell you. These are the important structures that can be asked in your exam. The first important structure is of your boric acid. This is BOH3 or your H3BO3 compound, right? So boric acid has a structure like this, and in between this there is a presence of H bonding. Can everybody see here, है ना? So what is the structure of boron here? Boron is actually attached to 1, 2, 3 molecules. So hence boron is actually sp2 hybridized. This is a planar structure with H bonding. So all these things you should know about the orthoboric acid. It is a planar structure. Boron is sp2 hybridized, right? And the H bonding is present in between the molecules. This is the structure of orthoboric acid or H3BO3. The other thing that you should know about is if a structure like this is mentioned to you, what you will write? You will write that this is actually a acid. Remember this. Do not get confused, yeah, ma'am, OH is written, it should be a base. No. The examiner will write the structure like this just to confuse. So this is actually a orthoboric acid, which is a very, very weak acid. Why am I saying that? Because, for example, if I try to react orthoboric acid with water, what happens? It takes the OH from the water. It actually takes the OH from water, and what happens? It becomes a BOH4 minus molecule, and the H plus is actually given. The H plus is actually given by the water molecule. It appears that in this reaction the H plus is releasing. So it appears that boric acid here is actually an acid, but the proton is actually given by the water molecule, and it abstracts the OH negative from the water molecule and takes in itself. So this is the entire reaction that happens with boric acid. Simple, easy reaction. That's why I told you should know the structure and this easy reaction, that it is actually an acid, a weak acid, but the proton, the H plus, is given by the water molecule, and it itself abstracts the OH from the water molecule. Is this thing clear to everybody? Is this thing clear to everybody? Okay? The next is the structure of diborane. Why is it important? Because it is again a reaction which has two things, which is the boron and the hydrogen, which is there in your course. So this structure will and can come in your exam. What is the structure of diborane? The molecular formula is B2H6. Very, very important structure. So its structure actually looks like this. I'm going to draw another structure. With boron, there are two here like this, two boron atoms. With each boron atom, two hydrogens are attached, right? And here what is happening, bacha? Here a electron cloud just like this happens, and here the electron cloud is shared by one hydrogen. Okay? So this actually diboron actually has a very famous bonding which is called banana bonding. It is therefore a very important compound. So what is happening? What is happening? Can you see with this boron? I'm going to take with this color only. With this boron, this boron with this hydrogen, boron with this hydrogen, boron with this hydrogen, and boron with this hydrogen is what kind of compound? What kind of bonding is formed with these four hydrogens? So the boron actually forms four kind of simple two-center, two-electron bonds. Correct? So with four hydrogens, boron with four hydrogens form two-center, two-electron bond. It means what? It means that this between boron and hydrogen, there are two centers. The centers are boron and hydrogen, and two electrons are shared. Similarly, with this boron-hydrogen bond, there are two centers, this boron, and again two electrons are shared in between. So this kind of simple bonding that we talk about is called a two-center, two-electron bond, which is any kind of bonding that we talk about. But if you talk about the other thing is, bacha, what? The other is this boron and this hydrogen. What kind of bonding is between this? Can you see that there are three centers now? I'm going to change the color. I'm going to take this color. Now, can you see that there is one boron, two boron, and one hydrogen? So, there are how many centers now? There are 1, 2, 3 centers. Okay? So, with the two hydrogens, this is one hydrogen, this is the second hydrogen, right? So, with one hydrogen, it is forming how many? So, these are three centers. Can you see? 1, 2, 3. 3 center and just 2 electron bonds. Okay? Okay? So this is how these bonds are formed. So what is actually happening? Look at this structure once again. Here boron, what is the hybridization of boron? Each case it is sp3. This boron is also sp3 hybridized. This is also sp3 hybridized. Okay? So what is happening? Boron is present here. With two hydrogen, it is forming simple bonds. But with the other hydrogen, only one boron is sharing one electron, and with the other hydrogen, the other boron is sharing the electron. Okay? So what is happening? Only one electron by both the borons is being shared by one hydrogen. So one boron shares here, for example, the other boron will share its electron towards here. So it is forming a banana bond like structure. Now because I told you that boron here is sp3 hybridized, it means that B2H6, what is meant by this? It means that B2H6 is actually a non-planar structure. Non-planar structure. Why is it a non-planar structure? Because the boron is sp3 hybridized. So it means what? It means that these two banana bonds that I form, these are called the banana bonds. These are called banana bonds. So banana bonds are 3 center, 2 electron bonds which are actually above and below the plane. Due to that, the structure of B2H6 is non-planar. It is a 3 center, 2 electron bonds above and below the plane. Therefore, non-planar molecules, all the boron are sp3 hybridized. With the 4 hydrogens, it is forming a 2 center, 2 electron bond. With the other 2 hydrogen which are above and below the plane, it is actually forming a 3 center, 2 electron bonds. Is this thing clear to everybody? Yes, bacha, boron has no d orbital. When did I say it has a d orbital? It has no d orbital. Yes, it has no d orbital. Here also I am not saying there is any d orbital. When did I say that? Okay? Next. Everybody understood this? And this is another structure that you should know about. You will get in the PDF what are the angles. Here the angle is 97 degree. Here the angle is 120 degree. Okay? The 4 terminal hydrogens of borons lie in one plane, right? These terminal hydrogens which we talked about here, these terminal 1, 2, 3, 4, these terminal hydrogens in one plane, the other 2 are above and below the plane. That's what I told you. Okay, above there are 2 bridging, and these are called bridging hydrogen atoms, which are above and below the plane are called bridging hydrogen atoms. Is this thing clear to everybody? Okay, is this thing clear to everybody? Pavish is saying to explain again. Explain again. Okay, I'll explain one more time. B2H6, what is the structure? There are 2 boron. One boron I'm drawing here, the other boron I'm drawing here. Okay, now I'm drawing 4 hydrogens. 1 hydrogen, 2 hydrogen, 3 hydrogen and 4 hydrogen. Okay, now the bonding with these 4 hydrogens is a simple kind of bonding that you study every time. What is happening here? With this boron, with these 4 hydrogens, can you see these 4 hydrogens? The bonding is actually 2 center, 2 electron bonding. है ना? 2 center, 2 electron bond, which means what? This boron is shared by 2 electrons, right? And the 2 centers are hydrogen and boron. In this bond, the centers are boron and hydrogen, and this is called the 2 electron bond. Okay? So this kind of bonding is called 2 center, 2 electron bonding. But now we have 2 more hydrogens to attach. How will those hydrogens attach? These attach through a special kind of bonding called a banana bonding. So here 1 hydrogen will be there, here 1 hydrogen will be there, and this banana bonding, these 2 hydrogens which will be above and below the plane. What is happening? These 2 hydrogens will be above and below the plane, and the bonding here is called the banana bonding because it is 3 center 2 electron bond. What is happening in 3 center 2 electron? I'm again going to explain it to you like this. For example, this boron, which is, I'm giving it yellow color. For example, this boron is sharing 1 electron to this hydrogen, and this hydrogen is also sharing its 1 electron, right? So how many electrons are there? 2 electrons. Okay? Now we talk about the other boron. I'll take red color for that. Blue color. Okay? Now let's talk about this boron. Now this boron gives its electron to here, and this hydrogen again gives its electron to here. So can you see that although these are sharing 1 bond, but the electron to this hydrogen, only this boron shares electron, and to this hydrogen, only this boron shares the electron. So what is happening? This kind of bonding is called the banana bonding, which is above and below the plane, and to 1 hydrogen, only 1 boron shares. To this hydrogen, only 1 boron shares its electron. But the shared electron in the end is shared by all these compounds all together. Hence, it is called a 3 center 2 electron bond, which is called a banana bond. Everybody understood? Okay? So now these 2 hydrogens are actually above and below the plane. Okay? These are above and below the plane. The rest of the hydrogens, the 4 hydrogens, are in the plane. Here boron is actually sp3 hybridized. Everybody understood this point now? Did everyone understood? Did everyone understand? Okay? Abhi it's clear. You just need to know what is a banana bond, how many centers, how many electrons, that is it. That is it, and some bondings are present, what are the angles, because this can be important from the exam point of view. Ma'am, in diboron, both boron atoms same plane. But the boron atoms are sp3 hybridized. Okay? So we cannot discuss, so these are not planar molecules, not planar. sp3 is what? It is not planar, not in one plane. Okay? Okay, next. Okay, now who will answer this question? Which of the following compounds is not a protonic acid? Protonic acid means what? Which gives away H plus ion. Which of these does not give away H plus ion? Who can answer this? Who can answer this? Option A, B, C or D? Abhi I explain it to you. This is again AIPMT 2003 questions. See, I've added so many questions. 2003 and 2023, almost 20 years. Correct? 20 years. Who can answer this? Please, I'm looking at the chat box. Let me know the answer to this question. Who can answer this? A. Pavish Yadav, very, very good. Yes, boric acid or this orthoboric acid is not a protonic acid because the proton here is actually given by the water molecule, which I just discussed with you. Correct? Next 2022 question on your screen. Which of the following statement is not correct about diborane? Which of these is not correct? Number A, there are 3 center 2 electron bonds. Is this a correct statement? The 4 terminal BH bonds are 2 center 2 electron bonds. The 4 terminal hydrogen atoms and the 2 boron atoms lie in one plane. Both the boron atoms are sp2 hybridized. Which of these is not correct? Not correct. Who can answer me? Who can answer me? Who can answer me? I'm looking at the chat box. D, very, very good. Nancy D. Venki 3. No, bacha. Here, see, it is written the 4 terminal hydrogen atoms and the 2 boron atoms lie in one plane, which is true. Here boron, here the hydrogen, these are in one plane. The hydrogens over here are above and below the plane. I know the boron here is sp3 hybridized, right? But this structure and this structure are in one plane and only the hydrogen molecules are above and below the plane. Okay? So this is a true statement. The false statement is the boron atoms are sp2 hybridized. No, the boron atoms are actually sp3 hybridized. Hence, this is the incorrect statement. Okay? Everybody understood? This is the incorrect statement. Correct. Now, AIPMT 2010. Which of the following molecular hydrides is a Lewis acid? Which is a Lewis acid out of these 3? Who can tell me? NH3, H2O, B2H6 or CH4. Which of these is a Lewis acid? Lewis acid means what? It has, it can accept electrons. Which of these is electron deficient? Which of these? Who can answer this? Who can answer this? I'm looking at chat box. Venki 3, very, very good. Very, very good. B2H6 is a boron hydride. Boron hydrides are electron deficient, right? I just told you that the bonding between them is just 3 center 2 electron, which means it is deficient in electrons. The electrons are not complete. Hence, it is a very good Lewis acid. Correct, correct. Next, we are now going towards the group 14. Very, very important group. Group 14, which is the carbon family. We just discussed everything about the boron family. Now we have entered the carbon family. So I'm going to discuss each and every group in very much detail so that nothing is remaining, so that these notes are sufficient for your preparation. So we're going to touch group 14 right now. Okay, we are going to start group 14 right now. Now, what is group 14? Consists of carbon. So we're going to study the abundances which are given in NCERT. So carbon has 3 isotopes. The isotopes are carbon 12, carbon 13 and carbon 14. Okay? Carbon 14 is a radioactive isotope which has a very big half-life of 5,770 years, but it still is a isotope. It is a radioactive isotope. Abundance, it is the 17th most abundant element of carbon in the Earth's crust. Okay, what are the minerals it is found in? In elemental state. Element means what? In the non-elemental means without any impurity, without any compound formation. It is found as coal, graphite and diamond. Coal, graphite and diamond are just made of carbon and nothing else. Next is in combined state, in forms of compounds. In combined state, it is found as metal carbonates, as hydrocarbons. We all know so many hydrocarbons are there, as carbon dioxide gas, which is 0.03% in air. Okay, so in combined state also carbon is formed. in elemental or pure state. Diamond is what? Diamond is very, very pure. Teacher is wearing a diamond, right? Very, very pure. It is a pure state. And in combined state also it is found. Next is silicon. Silicon is extremely abundant. Your mitti, your sand is what? The sand that is everywhere contains so much of silica in it, which is this silicon, right? So it is the second most abundant element. It is 27.7% by mass after oxygen. In the Earth's crust, after oxygen, if something is so much abundant, is actually your silicon. And how it is present? It is formed in form of silica and silicates in your sand. Okay? Next is germanium, tin and lead. So germanium, tin and lead, bacha, germanium is found in traces. Tin and lead are found in some quantity. Germanium is very less. And tin is, what are the minerals? Very, very important these things are. They can be asked directly in exam. What are the minerals? What is the formula for that mineral? Very important. So tin is found as cassiterite, which is called tin oxide, and lead as galena. Galena you have been studying since you were very, very little kids, right? Which is PBS. PBS, it is a mineral for lead. Okay? Everybody understood this? Let us move forward. Let us move forward with the electronic configuration. I told you, it is very important to know the electronic configuration when we're studying any p block element. What is its outermost electronic configuration is NS2 NP2. Correct? Let me select one pen color. It is NS2 NP2. This is the outermost electronic configuration. But the inner electronic configuration keeps on changing. How can it change? For example, in germanium, first time d orbitals are introduced. Similarly, in Pb, first time f orbitals are introduced. So due to the introduction of d orbitals and f orbitals, what happens? These are poor shielders. Hence, so much effect on the physical property and the chemical property will be experienced. Physical property, for example, their atomic size will reduce because d and f orbitals are poor shielders, hence the size will reduce. If the size will reduce, the ionization energy will reduce, and due to that, the formation of oxidation state will be affected due to the presence of d and f orbitals. So the inner electronic configuration is very important. That the first time d orbitals are introduced in germanium and f orbitals are introduced in Pb. Okay, everybody understood this? Let us move forward with the atomic radii. So what is the order of atomic radii for your F block elements? For the C. So it is very simple. All the trends here are very, very easy. Here what's happening? The carbon, silicon, then it will be your germanium, tin and lead. Then it will be your germanium, tin and lead. So it is a very basic order. So as you go down the group, what is happening? The number of shells are increasing. If the number of shells are increasing, hence the size will increase. So the trend follows the same trend. There is no exception over here. The trend follows just like this. Okay, now let's go to the ionization energy. What happens to that? If I'm going down, the size is increasing. Hence, to take out the electron from the outermost shell is easy. As I'm going down, because it is too far away from the nucleus, not attracted, hence to take out the electron from the outermost shell is easiest. So as I go down, the ionization energy must decrease. Hence, the same trend is followed. So here, the trend is carbon has the most ionization energy, then it will be your silicon, then it will be your germanium. Okay? And here there is an exception that here it is actually lead and tin. One second. Here it is an exception which is, yes, here it is lead and then tin, right? So I'm again making a circle outside it. Again, why? Because in lead, what was happening? F orbitals were getting introduced. So due to the introduction of F orbitals, the ionization energy increases. Why? Because F orbitals are poor shielders, hence the outermost electron is closer to the nucleus, hence it is harder to take out the electron, right? What is ionization energy? When I want to take out the electron from the outermost shell, the energy required to take out the electron from the outermost shell is called the ionization energy, right? And hence, because due to the introduction of F orbital in Pb, its ionization energy actually increases. Why? Because F orbitals are poor shielders, hence the electron experiences attraction towards the nucleus. The ionization energy hence increases. Okay? ठीक है, next, should we move on to the next thing? Next is your electronegativity. Again, here carbon is a non-metal, right? So it will be the most electronegative element. So the electronegativity order is carbon, then it is your lead, okay? Then it is your lead, and then it is your silicon, which is equivalent to germanium, which is equivalent to tin, like this. Okay, so this is the electronegativity order. All of these actually have the same electronegativity, but carbon is more electronegative than Pb. Everybody understood this? This is the electronegativity order. Now, if I am to compare between the electronegativity of group 13 and your group 14, which one will be more electronegative? Electronegative means what? The tendency to attract electrons to itself. So which one will be more electronegative? Group 13 or group 14? Who can answer this? I'm looking at the chat box once again. Who can answer this? I'm looking at the chat box. I am looking at the chat box. Please answer my question, bacha logo. Can anybody tell me? I'm looking at the chat box. Answer. Okay, nobody is answering. I will tell you. ठीक है बच्चा? So group 14 is actually more electronegative. Nobody answered me. Group 14 is more electronegative. Why? Because as we are moving from group wise in a period, the electronegativity actually increases along a period, right? So that's why group 14 is more electronegative than a group 13. ठीक है? Everybody understood this? ठीक है? Now next is electropositive character, which is a metallic character that we're going to discuss. Carbon is a non-metal. Silicon and germanium are metalloids. First time metalloids are introduced. Their properties are in between metals and non-metals. You have been studying this since your 9th class. I'm not going to explain what are metalloids to you right now. Okay? And these silicon and germanium are used in semiconductor industry. Very, very important use. They are used to make semiconductors, and your tin and lead are actually metallic. So what trend are you following? We are following that as I'm going down the group, the metallic character is actually increasing, right? So as I'm going down the group, the metallic character is increasing. Okay? So metallic character is actually influenced by the electropositive character. Okay? Electropositive character. So that's what I said. As I'm going down the group, metallic character increases, right? So as I'm going down the group, the metallic character is actually, bacha, what is happening? The metallic character is actually increasing. Everybody remember this thing. The next thing that is happening, so it means what? It means your tin and lead are actually soft metals. What are these? These are actually soft metals. Okay? Soft metals with low melting point. So these are some facts that I'm going to tell you. Okay? Now, which is more metallic? Is group 13 more metallic? So, metallic character, I'm going to ask you, which is more metallic? Group 13 or group 14? Please answer this. Abhi I told you about electronegativity, right? So, which was more electronegative? Group 14. So, now tell me, which is more metallic in character? Is it group 13 or group 14? Who can tell me? Who can tell me? So, group 13 will be the more metallic character, which will be the more metallic group, right? Right? Now, moving on to the next, oxidation state. So, again, I'm going to draw that each electronic configuration is NS2, NP2. Okay? So, this is the electronic configuration. So, how many oxidation state can it show? It can actually show when all the electrons from the p orbitals go away. So it can show either +2 oxidation state, or when p plus s, all these electrons go away, then it can show +4 oxidation state as well. Correct? So two kinds of oxidation state can show +2 as well as +4. Now let us see one by one which oxidation states are shown. With carbon, it will show mostly +4 oxidation state and sometimes -4. -4 means what? It can, if the p orbital gets 4 more electrons inside it, then it will become ns2np6. Again, it's octet, it's complete, right? So it can either show +4 or -4 oxidation state, correct? Or +4 to -4, I can also write. The silicon only show +4 oxidation state. Germanium, tin and lead shows +2 and +4 oxidation states. Remember this thing. Again, the same things I'm going to tell you, because +4 means what? You have to take out 4 electrons one by one. 1 electron, 1 ionization energy. Second ionization, third ionization energy, fourth ionization energy. So to take out 4 electrons and to make it an ionic compound, I have to give it 4 ionization energy, which is so much. Hence +4. Hence +4 oxidation state compounds only and only form covalent compounds, because 4 ionization energy is too much to give, right? So +4 will always form covalent compounds, because why? Because sum of ionization energy 1, ionization energy 2, ionization energy 3, ionization energy 4 is very high. Hence it will never form ionic compounds. It will only form covalent compounds in +4 oxidation state. Okay, again, the next thing that I always discussed is, as I'm moving down the group, it is showing how many oxidation state? It is showing +4 and +2 oxidation state, right? So as I'm going down the group, what is happening? Stability of +4 oxidation state decreases, right? But +2 oxidation state increases. Why? Due to the inert pair effect, right? I just discussed with you what is inert pair effect, because d orbitals from here and f orbitals from here are introduced, right? So due to the d and f orbitals, what actually happens? The s orbital, the configuration was ns2 and p2. So due to the introduction of d and f orbitals, the s orbitals now do not participate in bonding. I just explained to you what the inert pair effect was. So when d and f orbitals are introduced, the s orbitals do not participate in bonding. Hence, these 2 electrons will not participate in oxidation state. Only p electrons will participate. Hence, +2 oxidation state will be stable for Pb, while +4 will be stable for carbon. Okay? So now I'm writing the stability order over here. Stability order. Can I write it over here? Can everybody see? So the stability order is germanium +4 is more stable than tin +4, right? Is more stable than Pb +4. Similarly, germanium +2 is least stable than tin +2, and Pb +2 bacha is the most stable compound. Everybody understood this? Everybody understood this? Hence, the next thing that I can say is, if any compound is present in the form of Pb +4, if any compound is formed in the presence of Pb +4, for example, PbO2 is present. In PbO2, Pb is actually in +4 oxidation state, right? So what is happening? In Pb +4, Pb is actually in +4 oxidation state, but we know that Pb is stable in +2. So Pb will want to convert into +2 oxidation state. It wants to get reduced. Hence, Pb +4 will always wants to get reduced to Pb +2. Hence, Pb +4 will act as a good oxidizing agent, which I just told you, right? It will act as a very, very good oxidizing agent, because it will always want to convert into Pb +2 oxidation state. Okay, everybody understood this? Everybody understood this? Okay? Okay? Shall I move on to the next thing, bacha? Shall I move on to the next thing? Next oxidation state that we're going to consider is the how many covalencies can it form. So the bacha, carbon, maximum covalency that carbon can show. I'm writing it here. Carbon covalence. valency. The maximum covalency carbon can show is 4 because carbon do not have any d orbitals. It only has p orbitals. Hence, the maximum covalency it can show is 4. Okay? The next is from silicon, germanium, tin and lead. It can expand because from silicon, d orbitals are present. Hence, it can expand its covalency. Hence, more than 4 bonds are formed. For example, silicon F6, 2 minus can be formed. Similarly, germanium Cl6, 2 minus can be formed. So, these compounds actually exist. Just remember this thing. For example, tin hydroxide 6, 2 minus can be formed. So, all these actually exist. All these compounds actually exist. So, this is the next point that I want to tell you. Next is the melting point and boiling point. Again told you, boiling point depends on the size, while melting point depends only on its crystal structure, right? So, what will be the boiling point and melting point order? So, bacha, the boiling point order is actually silicon has the highest boiling point, then it is germanium, then it is tin, and then it is lead. Similarly, the melting point order that is followed is carbon has the highest, then silicon, then it is germanium, then it is lead, and then it is tin. So these orders but are extremely important. I'm circling all the exceptions over here. This is the boiling point order. This is the melting point order. Only the values are given in your NCERT, right? I have made trends out of these values. These trends are based on the NCERT values itself. I have not taken it from any other book because in your, no matter what exam you're taking, the board exam or your NEET exam or your JEE exam, it only and only follows NCERT. Hence, all the NCERT orders I've written over here only follow these orders. Okay? And I'm going to tell you another thing, bacha, here the PB actually has a higher melting point. I told you. The melting point depends upon the crystal structure, and the PB here actually has a very complex crystal structure. What kind? That it forms a distorted 12 coordinated structure. It forms a distorted 12 coordinated structure, right? But all these things are actually mentioned in your NCERT, hence I'm telling you here. So they form a distorted 12 coordinated structure. Hence this is formed. Okay, everybody understood? Now the next is your density. Again, density is mass upon volume. What is the trend for density? Again, it is carbon, silicon, germanium, tin and lead. Okay, tin and lead. Okay, and here which form of carbon I have used, because carbon is a allotrope. It can be graphite, it can be fullerene, it can be diamond. So here the density of graphite is considered, right? So I have compared the density of graphite with other things, and the carbon has the least density, because then you will be, ma'am, diamond is the hardest substance, it has the highest density, right? That could be your point of argument, right? So here that's why I'm telling you ki here graphite is considered for calculating the density in this case, because obviously, because a diamond is the hardest metal, it's gonna have the highest density as well. Correct? Everybody understood these points? These points. Now, bacha, what we're going to do, it's already 5:30. It's already 5:30. Now, do you want to read about the reactivities right now, or do you want to give it another day? Do you want to give it another day? Just let me know in the chat box. I'm seeing bache in the chat box. I can complete the 14th group even right now, or we can continue it in the next class. But I think we should continue it right now only. Okay? Now the reactivity towards oxygen. What I'm doing, I'm taking these elements and trying to react them with oxygen. What kind of compounds they can form with oxygen? We're going to discuss those. So they form actually two kinds of oxides. One second. Okay, this hanged. This hanged. Can you see me? Why is this hanging? Okay, the board itself hanged. The board itself hanged. Okay, if you can still see me, I'm sorry. The board hanged at this point, at the junction of point. I don't know why. Then we will continue from the reactions, from the reactivity of carbon in our next lecture, whenever it happens in the next week. Probably you will get the schedule and we will complete group 14 and group 15 then. So why it took so much time today? Because I was explaining to you the P block and then we entered into the 13th group. Hai na? So right now I explained each and everything in detail. In the next classes, what are going to happen? Now we know most of the basic things. We know what is the inert pair effect. What do I mean by the oxidation state? When I go down the lower oxidation state, actually stability increases. The higher oxidation state stability is the most for the topmost elements. Why are the anomalous properties shown? So now we know all these things. We are familiar with these trends, right? So we just have to use these things in the next P block things, and we're going to study all the structures of the group 14 plus the group 15, whatever is left right now. We're going to complete because right now the board itself hanged. I don't know why the God doesn't want you students. They just want you to complete in the next lecture probably. So we're going to do that. But please revise all these things, and that is my guarantee that after attending my lecture, you do not need to follow any NCERT after that. You do not need to even open your NCERT books because I've included each and everything from NCERT here, which I've included the screenshots over here, as you could see, in the form of questions or whatever. So we're going to complete everything in these lecture series. Just have faith in your Nandini ma'am, and we're going to complete our session here, right? Right, I think we should end the lecture here. Thank you for attending my class. Tara, goodbye. I will see you soon. And please like the session, subscribe to the channel. Whatever feedback you have for the session, let me know. Bye-bye. Thank you.